Today's lecture, I have introduced one more additional topic, that is on industrial furnaces. Now, considering the importance of furnaces, I thought that it will be an appropriate to give you some account of the material and heat balance in industrial furnaces, because for high temperature operations, whether they are performed below the melting point of the material or above the melting point of material, the furnaces play a very important role. Furnaces also play an important role, particularly for high temperature applications, the consumption of energy and also the emissions of carbon dioxide, as I will try to illustrate both the aspects in this particular lecture. So, let us see first of all what is meant by a furnace. In fact, what I want to define a furnace, I want to say a furnace is a thermal enclosure, is a thermal enclosure, and is employed to heat the material below or above its melting point. Now, there are certain examples. For example, examples of furnaces that are employed to heat the material below the melting point, those furnaces they are used to perform, for example, thermomechanical processing. What I mean under this, that when a material is mechanically processed, then material is heated at high temperature, and for that furnaces are used. The reasons are obvious, because the material becomes plastic at that particular temperature, so that the mechanical processing are easier. So, one of the important application of furnaces is to heat the material below the melting point for thermomechanical processing. Thermomechanical processing, that could be rolling, that could be forging, you must have heard hot forging, or that could be an extrusion. Here the objective is to heat the material below the melting point. For example, steel, it is often heated between 1000 and 1200 degrees Celsius, and copper, aluminum below their respective melting point. It is one of the important objective of the furnace. Another example is for heat treatment, for the heat treatment purposes. Now, for the heat treatment purposes, again the materials are heated, of course, below the melting point, and then they are cooled. I have no intention to deal or to go into the details of heat treatment, but the various operations under heat treatment, they are, for example, annealing. Now, in annealing, material is heated below the melting point in the furnace and cooled in the furnace. Then normalizing, material is cooled outside the furnace in the air, and quenching. Of course, there are other operations, but for this particular lecture, what I wanted to say, the different objectives of the furnaces. There is still another objective of the furnace, is that of sintering. Say in various powder metallurgical operations and ceramic processing, you heat the material for sintering operations, so that you develop an appropriate strength. Now, here itself, if I want to extend the application of furnaces because I defined as a thermal enclosure, then a very important function of the furnaces is for processing the material above the melting point, as we have seen in the all lectures on material and heat balance. The thermal enclosure like matte smelter, like roaster, like blast furnace and so on. So, there you heat the material above the melting point of the material. So, now here specifically I will go in detail to the material and heat balance of the industrial furnaces which are employed below the melting point of the material, keeping in view the energy requirement and carbon emissions into the environment. These are the two objectives. Now, in this connection, just to give you an idea, the types of furnaces, there are normally two types of furnaces. Furnaces can be classified in various ways, continuous and batch furnaces. In continuous furnaces, there is a constant input and constant output. In batch, you heat the material for certain time, and after certain time the material is out. So, this is the, you can also classify the furnaces on the way in which the furnaces are used. For example, if the furnace is used for annealing, you call this is a annealing furnace. A furnace is used for rolling or for forging, you call forging furnace, but essentially they are all thermal enclosure. Now, in this particular connection, it is also important to see the source of energy with which we are concerned in this particular lecture. Particularly if you heat the material, for example, steel, you heat about 1200 degrees Celsius. So, let us see the sources of energy or source of energy, source of thermal energy. Now, source of thermal energy is a combustion of fossil fuel, combustion of fossil fuels. Now, under fossil fuel we have coal, we have natural gas, and an important fuel is oil. It is derived from petroleum, that is why I am not putting under fossil fuel, but the derivative of petroleum, that is an oil. Again, I will again mention that oil is derived from petroleum, but oil is frequently used in high temperature furnaces. So, these are the sources of energy. Another important source of energy is electric energy, but as long as electric energy is derived from combustion of fossil fuel, so one can say electric energy is also dependent upon the use of fossil fuel. Around 70 to 75% of the electrical energy requirement is being met from combustion of fossil fuel, that is particularly coal. You use electrical energy, you say that I am using electrical energy, but it is coming from somewhere where fossil fuel is used to generate electrical energy. Around 70 to 75% is the contribution of the electrical energy out of the for the total energy consumption. Now, having known the source of thermal energy, which is the fossil fuel, now the natural question comes before us. The question which I am posing, how is thermal energy derived from fossil fuel? How is thermal energy derived from fossil fuel? Because fossil fuel, it contains potential energy. You bring the fuel from the mines, put it on the earth, it has energy, but it has only potential energy. So, the potential energy of the fuel, you have to convert it for the useful energy. So, the thermal energy from fossil fuel is derived by combustion of fuel. By combustion of fuel, the potential energy of the fuel is obtained in order to heat the furnace or anything at a particular temperature. Now, what is that involved in the combustion of fuel? Now, as we see, the fossil fuel, they are containing most of the time a large amount of carbon. For example, coal, it has a good quality coal, it has 75 to 80% of carbon, oil 85 to 86% of carbon, hydrogen is very, very less. In natural gas, you also have CH4, though hydrogen is there, but still carbon is sufficient amount. Therefore, it is important to know how thermal energy is obtained. So, what is being done is that the potential energy of the fuel, potential energy of fuel is converted into sensible heat of products of combustion into sensible heat of products of combustion and these products of combustion, they heat the furnace, or so called material which is required to be heated, and then after heating the products of combustion, they discharge the furnace. They are discharged into surrounding at a temperature which is equal to, at least equal to the furnace temperature. So, if I can represent, for example, if this is a furnace, just an enclosure, and if I supply here a fuel which contains potential energy, I combust with air. Suppose the temperature T here, which is say 1000 degrees Celsius, then on combustion the potential energy of the fuel is converted into sensible heat of products of combustion. There is a heat exchange occurs between the products of combustion and the furnace enclosure, and then the products of combustion exit the furnace. The products of combustion POC, which I call products of combustion, exit the furnace. What does it mean? That means, if the temperature of the furnace is say for example 1200 degrees Celsius, then the minimum temperature of the products of combustion that are exiting the furnace has to be equal to, at least equal to 1200 degrees Celsius. If the temperature of the furnace is 1300 degrees Celsius, then the temperature of POC which is exiting the furnace, it has to be around 1300 degrees Celsius. What does it mean? That means, the energy leaving with POC, say energy leaving with POC is not available, to perform any thermal energy operation inside the furnace. So, higher is the temperature of the furnace, higher will be the energy leaving with POC, and that is not available. So, therefore, we can define now two important parameter. One, we say gross available heat, gross available heat, which I will call GAH, that is equal to calorific value of fuel, calorific value of fuel minus heat carried by products of combustion. There is also an important term here, because when you construct the thermal enclosure, then what you do, you put an insulating here. So, this is a insulating wall, this is a insulating wall, you provide an insulation, and through the insulation there will also be heat losses. There will also be heat losses. So, then another term is defined that is called net available heat. Net available heat, in short I will call NAH, that will be equal to gross available heat minus heat lost from walls of the furnace. Now, this heat loss through the walls of the furnace, say heat loss, that can be very easily calculated, say amount of Q, which is the heat loss, from minus K A dt by dx, which is the Fourier's law of heat conduction. T is the temperature of the furnace wall and x is the thickness of the lining. If we have multi-layered wall, because you can construct a wall not by a single material, but you can construct by 2 or 3 different materials. So, that is called a multi-layered wall of thermal conductivity is K 1, K 2 and so on, and their thickness let us say L 1, L 2 and so on. Then we can define the heat loss, that will be equal to T I, which is the furnace temperature, minus T 0, that is the surrounding temperature, upon thermal resistances, which is H I, where H I is the heat transfer coefficient from the combustion chamber to the wall, plus thermal resistance offered by the multi-layered lining, that is equal to L I upon K I, where this is I is equal to 1 to n, plus 1 upon H 0 into A, where H 0 is the heat transfer coefficient from the wall to the surrounding. T 0 is the temperature of the surrounding and T I is the temperature of the combustion chamber, that is you can calculate the heat loss. This is for the multi-layered lining. Now, given that there is a large amount of heat loss from the furnace, if we want to utilize the heat or the calorific value of the fuel, what is to be done? Because the calorific value of the fuel, which is the potential energy, you wanted to obtain its thermal energy, you have combusted and you have noted that if the higher is the temperature, more amount of heat is being lost. So, what the question that emerges for efficient utilization of fuel, for efficient utilization of fuel, what is to be done? That is, heat which is exiting with the POC, it must be captured and then reused. So, for efficient utilization of fuel, capturing of the heat, and its utilization is important, because by capturing the heat and its utilization, for example, back into the furnace, you are able to reduce the amount of fuel which are consumed, and at the same time you will be saving the fuel, and as a result you will be consuming less fuel. So, less carbon will be emitted. So, by capturing the heat, you are hitting 2 birds with a single stone. You are reducing the fuel consumption, that means you are contributing to the energy security, you are saving the fuel, and since you are saving the fuel, you are doing less emissions of carbon into the environment, that is you are contributing to the so called environment sustainability, and both these aspects I will illustrate by giving a suitable example. Now, say when we say that the capturing of the heat is important, then we have to think how to capture the heat. Say in the basic philosophy of capturing the heat is say designing a heat exchanger. designing a heat exchanger. Now, naturally in this course I may not be able to go into the details of heat exchanger. I request you to please see my lectures on fuels, refractory and furnaces. There I have detailed the heat exchanger. I will here just give you the gist, so that I can use to illustrate the thing. Now, imagine you have a heat exchanger. So, in the heat exchanger a hot fluid is flowing, for example, at temperature TH1, it is being out at TH2 and you have separated the hot fluid by a through a wall. Suppose this is a wall, here the cold fluid is entering, for example, air, say air, and hot air is being discharged, and that can be used for heating into the furnace. So, you can imagine a heat exchanger where hot flue gases is flowing counter current to the flow of air. So, this is typically a so called counter current heat exchanger. Now, how the heat is being exchanged? As the hot fluid passes, the separating wall gets heated up, it transfers heat to the flowing cold air. So, it is essentially the flow rate of the fluid, that is flow rate of both the fluids, flow rate of both fluids, thermal resistance of the separating wall, thermal resistance of the separating wall, because if it is more resistance, less heat will be given to the colder fluid and less will be heated up. Thermal resistance of the wall is also an important, and another important thing is that the differences in heat capacities, differences in heat capacities. These three will decide how high a flue gas can heat the cold fluid to a temperature. Of course, higher is the temperature, better is this, but then there is a thermodynamic limit. A flue gas which is passing at a temperature T, it cannot heat the cold air at a temperature greater than T. It is not thermodynamically, it is not possible. So, therefore, we can define certain efficiencies. We can define certain efficiencies. Say, one we define overall thermal efficiency, overall thermal efficiency, that is defined, say sensible heat in heated air, sensible heat in heated air upon sensible heat in hot flue gas, sensible heat in hot flue gas, of course multiply by 100. Now, in this particular definition, it is inbuilt that air, it can be heated above the temperature of the hot fluid, which is thermodynamically not possible. Therefore, another limit is defined, that is called efficiency limit. And efficiency limit that can be defined, sensible heat in air, sensible heat in air at hot flue gas temperature, there is a maximum you can get, hot flue gas temperature divided by sensible heat in hot flue gas. Of course, you have to multiply by 100 to get the percentage. Well, if you want to put it in a formula, M A is the mass flow rate of air, C P A is the heat capacity of the air, and T F is the temperature of the hot flue gas, and 25 is the reference limit or the reference temperature, Similarly, mH is the mass flow rate of hot fluid, Cph is the heat capacity of the hot fluid or the flue gas, and it is at temperature Tf. So, the maximum heat that you can, or the sensible heat in hot flue gas, that will be minus 25, where 25 degree Celsius is the reference temperature of my calculation. You can also take 298 Kelvin, that does not matter at all, of course into 100. So, you can see this both cancels out, and ultimately efficiency limit, it is the ratio of the heat capacities of cold and hot fluid. Then we define a relative efficiency, that means if you want to compare the two exchangers at different location, then it is equal to overall thermal efficiency upon efficiency limit. Into 100. So, this definition relative efficiency, that is equal to overall thermal efficiency upon efficiency limit into 100, it can be used as a parameter to compare the heat exchangers of two locations, because if we substitute the overall thermal efficiency and efficiency limit, then it simply turns out to be equal to sensible heat in air upon sensible heat in air at hot flue gas temperature. So, that is how the efficiency of the heat exchanger can be calculated. Now, I will simply explain by illustrating a problem. Say for example, let us say a heat exchanger, let us consider a heat exchanger receives hot flue gas, say hot flue gas at 1600 Kelvin and cold air at 298 Kelvin, because in this thermodynamic definition it is inbuilt that whether the flow is counter current or co-current, the efficiencies are not affected, there is no kinetics will be affected. Now, the hot flue gases leave the exchanger at 900 Kelvin and cold air is heated to 1373 Kelvin. That means, air is leaving the exchanger at 1373 Kelvin. It is also said that 15% of the heat of the flue gas is lost to the surrounding. That means what? That means 85% of the heat of the flue gas is recovered to heat the air to the temperature which is 1373 Kelvin. It is also given Cph, that is Cp of hot flue gas upon Cp air, its ratio is given to 1.2, which is say for this problem independent of temperature. So, let us do the heat balance. Now, let me illustrate the efficiency and so on. So, to solve this problem, let us do first of all heat balance. What this heat balance says, that only 85% of the heat of the flue gas is recovered in air. So, that means 0.85 mH is the flow rate of the hot flue gas, Cph heat capacity of the hot flue gas into Th1 minus Th2, that is equal to mc Cpc Tc2 minus Tc1. So, if I substitute, then I will be getting say 0.85 mH CPH 1600 minus 1900 MC CPC 1373 minus 298. So, if I solve, then I will be getting say MC CPC upon MH CPH, this ratio, that is equal to 0.55. Now, with this ratio I can now proceed to calculate the various efficiency. So, first let me calculate overall thermal efficiency. Overall thermal efficiency, as already I have defined. So, straight away I will be using the formula, that is equal to MC CPC 1373 minus 298 upon MH CPH 1600 minus 298. So, into of course, into 100, that will be equal to let us say 0.55 into 1075 divided by 1302 into 100. So, overall thermal efficiency is 45.44%. So, that is how you will be calculating in the problems whenever you come across to calculate the efficiency of the heat exchanger. Now, another thing is that to calculate, let us calculate efficiency limit. Efficiency limit. Now, the physical significance of efficient limit is very clear. That means, each heat exchanger has some upper limit to which it can exchange the heat of the hot flue gas to the cold flue gas thermodynamically, because you cannot heat the cold air to a temperature above the temperature of the hot flue gas. Thermodynamically, it is impossible. That is what the physical significance of efficiency limit is, and we have seen in the formula that the efficiency limit, it simply becomes equal to MC CPC upon MH into CPH into 100. The temperature from both the sides, numerator and denominator, they cancels it. So, the efficiency limit in this particular case, that is equal to 55%. That means, in this particular problem, the efficiency limit of that designed heat exchanger is only 55%, and that depends totally on the difference in the heat capacities. Higher is the difference, less will be the efficiency limit. So, that is all. So, then we define another term, which is the relative efficiency, which is the relative efficiency, and the relative efficiency you define overall thermal efficiency divided by the efficiency limit into 100. So, with this we get 45.4 upon 55 into 100. So, your efficiency limit is now 82.5%. That is how you can calculate the efficiencies of heat exchanger, because in several calculation, when you want to capture the heat and you want to recycle the heat for the heating of air, and the preheated air is supplied in the furnace, then you must be able to calculate what is the efficiency of the heat exchanger. Then you have to calculate the efficiency of the heat exchanger with one of the formula that I have given. This is one illustration. Now, another illustration that I am going to illustrate on the fuel saving and the carbon credit. So, let me take the next problem, that is the illustration of available heat, say illustration of available heat fuel saving, and let me touch also carbon credit. Let us see how we can calculate all this. Now, for this naturally we have to perform heat balance and material balance. Now, for that let us consider a furnace. Say let us consider a furnace. The furnace, it is operating at 1227 degrees Celsius, that is the temperature of the combustion chamber of the furnace is 1227 degrees Celsius. This furnace is oil fired, and the composition of the oil, carbon, that is equal to 88%, hydrogen, that is equal to 11%, and oxygen, that is equal to 1%. It is also given the gross calorific value of fuel is given, gross calorific value of fuel that is given to you, and that is equal to 10,830 kilocalorie per kg of the fuel. The products of combustion, the POC, I am writing short form of products of combustion, their percent is given volume percent dry, and this composition is CO2, CO, O2 and nitrogen. CO2 is 12.7%, this is 1.5%, O2 3.3% and nitrogen is 82.5%. It is combusted with air, and now we have to calculate the various available heat, fuel saving and so on. Now, for this purpose what we will do, let us take say 1 kg is the basis of our calculation. 1 kg fuel is our basis of calculation. Now, since we are going to perform heat balance also, so it is also important to mention the temperature at which the materials are leaving and exiting the furnace. For this purpose I am considering that the temperature of supply of the oil is, let us say, 25 degrees Celsius. The products of combustion, they are discharging at temperature T, that is equal to 1227 degrees Celsius for the temperature of discharge. Now, 1 kg fuel is the basis of calculation. So, first of all, let us calculate say gross available heat per kg of fuel. Now, as you have noted down in the problem that the products of combustion contains carbon monoxide, that means there is an incomplete combustion. So, in the part A what we are going to calculate is the gross available heat per kg of the fuel as given in the problem. So, but the note is that there is an incomplete combustion because CO is in POC. So, first of all let us consider say Y kg mole is POC, Y kg mole is amount of POC. Then on several occasions we have done carbon balance. So, if I do carbon balance I can find out the amount of POC. So, if I do carbon balance, so carbon balance will give me the amount of POC Y that is equal to 0.516 kg mole. Now, once I have gotten the amount of POC which is 0.516 kg mole, now I can calculate the amount of CO2, the amount of CO, O2, nitrogen. Do not forget to calculate hydrogen which is coming exclusively from hydrogen of the oil. So, you have to make that also into your calculation to make the products of combustion complete. Now, the next thing that we have to calculate is heat to POC. In order to calculate heat to POC, what is required is that you should know the value of the heat content, that is the sensible heat of CO2 or the heat content of CO2 at 1227 degrees Celsius. What I have done, I am giving you the value of products of combustion at the temperature at which they are discharged. The reference point in all thermodynamic values is 298 Kelvin or 25 degrees Celsius. So, as such I am giving you here H 1500 minus H 298 for CO2, that is equal to 14780, that is in kilocalorie per kg mole. Similarly, H 1500 minus H 298 for CO, for O2, then for N2 and for H2O liquid. All you can calculate from their Cp value. CO, that is 9291, 9791, 9186 and 22034. So, once these values are given to us, then we can calculate the heat to POC, and heat to POC will be simply the moles of the products of combustion multiplied by the respective value of the sensible heat. So, we get now heat to POC, that will be 14780 into 0.0656 plus 0.00774 into 9291 plus 9711 into 0.01703 plus 0.4257 into 9186 plus 0.055, 0.055 is coming H2H2O of the fuel into 220,234. So, heat to POC, that will be 6330 kilocalorie. So, that is how you can calculate the heat to POC. Now, important thing here, while calculating the calorific value of the fuel, because the gross available heat per kg of the fuel is the calorific value minus heat to POC. In this particular section A, which we are calculating when the products of combustion contains carbon monoxide, we cannot use the gross calorific value which is given, which is 10,830 kilocalorie per kg, because this value is given on complete combustion. But part of the combustion is not complete because CO is there. So, you have to subtract the calorific value, mind you, the calorific value of CO from the gross calorific value of the fuel which is given to you. So, that brings us say GCV of fuel, that is equal to GCV, which is GCV of fuel on incomplete combustion in our problem, on incomplete combustion, that will be equal to GCV, which is given for complete combustion minus calorific value of carbon monoxide. So, that is an important thing. Now, the calorific value of carbon monoxide you can calculate, say CO plus half O2, that is equal to CO2. So, minus delta H naught, say combustion, that will be equal to 67.6 into 10 to the power 3 kilocalorie per kg mole. That is how, because heat of formation of CO2 is subtract from heat of formation of CO, and then you get 67.6 into 10 to the power 3. So, what we will do now, GCV given is 10,830 minus calorific value of CO you have to subtract, that will be 0.00774 into 67.6 into 10 to the power 3. So, that brings to us the gross caloric value available for A, that is 10,307 kilocalorie. Now, the next we have to calculate the gross available heat, that is what is being asked. So, I will put it, let us calculate gross available heat 1, that will be equal to 10,307 minus 6330, that is equal to 3977 kilocalorie. Now, in order to compare this B part, let us consider now complete combustion. Let us consider complete combustion with same air fuel ratio as we have employed in part A. We have not changed any air fuel ratio, only because of better mixing we could obtain complete combustion. Now, let us calculate now for this case what will be the gross available heat. Let me put that is equal to 2. Now, since now I am mentioning complete combustion, so that means CO will not be there. So, I have to recalculate the products of combustion. The products of combustion will be now CO2, that will be equal to 0.07334 kg moles, because here I have to add CO2 which was originally and CO moles also. Then now, since the oxygen which was there in case A in the products of combustion, partly it will be utilized to combust CO. So, now the oxygen in POC will be less. So, that will be equal to 0.01316. Nitrogen of course, will not change because we are not changing the air fuel ratio, that will be 0.4257. Now, we have got the renewed moles of products of combustion, they are exiting at the temperature we are taking the same 1227 degrees Celsius. Now, we can calculate the gross available heat 2. What we have to do? The gross caloric value will remain the same because it will not change, only heat to POC you have to calculate. I have already given you the values of the various products of combustion at 1227 or 1500 Kelvin. So, you can calculate those values, and on calculation the heat to POC in this particular case, heat to POC in this particular case, this comes out to be equal to 6328 kilocalories. So, now the gross available heat 2, which is for complete combustion, that will be equal to 10,830 minus 6,328. So, that will be 4,502 kilocalorie. So, you are seeing there is an increase in the gross available heat by just doing a good mixing in the combustion chamber on complete combustion. So, now we can calculate, say C part we will calculate, say fuel saving on complete combustion. Now, we can define now, say fuel consumption is normally defined in kilogram per hour. It can be defined as, say, gross available heat required per hour upon gross available heat per kg of fuel. So, now we can calculate F1, which is the fuel consumption due to incomplete combustion, that will be equal to, now the gross available heat required per hour will be same, and gross available heat per kg of the fuel. So, I will put it gross available heat required per hour upon, in the first case we have 3977. We can calculate now F2, that is equal to, for complete combustion. So, G gross available heat required per hour divided by 4502. Now, since the furnace is operating at the requirement of the gross availability same in both the cases. So, therefore, what we can do, we can take the ratio of F1 upon F2, the ratio of F1 upon F2, that is ratio that is equal to 4502 upon 3977. So, with this now fuel saving, that of course, 1 minus this and multiply by 100, that is equal to 13.2%. So, you can see just by introducing the measure of complete combustion, you are able to save 13.2% of the fuel. Now, just to illustrate the concept of carbon credit, now for example, if we consider, say, if 10,000 kg is the fuel consumption, okay, then fuel saving will be how much? 13.2% per kg. So, for 10,000 it will be 1320 kg. So, you will be saving 1320 kg fuel on account of complete combustion. Now, about the carbon credit, it is said that 1 metric ton of CO2 reduction is equivalent to 1 carbon credit or offset, and is equivalent to 270 kg carbon. That means, if you are saving 270 kg of carbon, then you are earning 1 carbon credit. So, carbon credit in this case would be carbon credit that would be on account of complete combustion in this particular problem, that will be approximately 1320 by 270, it will be approximately 5. So, that is what, how the fuel saving can lead to simultaneously two things: saving of fuel, which leads to energy security, and reduction in the carbon emission into the environment, that is contributes to the environment sustainability. In the next lecture, I am going to give you more problems on the industrial furnaces.